Previously, I had looked at some Leisen Reimer estimation. I went back to the original Leisen Reimer paper. This particular draft is from 1995, and then I'm looking more closely at the results reported in Table 1, which is on page 18, 18 of in this paper. So the parameter values we have here: stock price is 100, risk-free rate 7%, and volatility equal to 30%, T is equal to 6 months, and N is equal to 25. And I have three models set up here in C++. One that's static. In other words, we use a static binomial tree. Another model where Leisen Reimer binomial is nested in a dynamic tree, which is a bit faster. And then the third tree is a Leisen Reimer binomial nested in a dynamic tree, but the zeros from the tree are truncated. And we'll take a look at the speed in terms of computation. So the values here, let's set out then the code side by side with the results that we have here, and just verify that the model is working, that the C++ code is robust. So in the first instance, I have this code here. It's static code, and InQ developed a static type binomial framework for estimating options, and he used some of the volupta code in order to make the estimation. Importantly, here in this estimation, we're using this type of tree, which generally implies that we're storing all the nodes, every stock price that is generated in the tree associated with every node is stored, and then that has to be pulled down subsequently when we estimate the intrinsic value of the option, and then when we perform the backward recursion. And okay, if we change so let's I'll pause here and set both sets of code up side by side. Okay, so basically we have the same code, S100, the spot price of the stock is 100, the risk-free rate is 7%, the volatility is 30%, 6 months to maturity, and we'll change N to 25. So we'll take out this 5,000 and put in place 25, and we will run and then compare the results. Now again, this is okay, so what we get here is 59488, and looking at this, we have 594,889, right? So basically when you round here, it gets the same result. I'm going to take another look then at the next model, which is a dynamic model. And in the dynamic model, we don't have a static tree, we have a dynamic tree. And so basically the same structure, the same type of design here in estimating the parameter, taking the parameter inputs and then working out D1, D2, U, D, P, so on, exactly the same as before. But in this instance, the tree is dynamic, so the memory passes. We don't estimate a static tree, we estimate a dynamic tree. And again, all we need to do is change our parameter input here from being 5,000 to 25, and run this. Again, it's for a call, and it's American, European or American will yield the same result, but we have 594,889, so the result is the same. The only difference is in terms of the estimation time, but the result is the same. And then the third result, again, it's in this instance we're using a dynamic tree design, but we're also truncating the zeros. from so again, the same basic estimation, D1, D2, P, U, D, all estimate the same way. It's a dynamic type structure, and then we have to truncate the tree, and we'll look a little bit more closely at how that's performed. Now when I say truncate the tree, it means we cut out the zeros from the tree, and then we run the estimation. The only value I need to change here is to change this to 25. Let's run that and observe what the output is, and we get 59488886329, and again the result is the same as the preceding result, 594888 for and also for the static. So the static tree, the dynamic tree, and the truncated dynamic tree, all three results are the same and consistent with Leisen and Reimer. Okay, we can just do one more test. If I change the A here to P, this is for the dynamic truncated tree, so it's a put option. We run that estimation. Oops, that won't work, shouldn't work. It should be here A, but for a put option P. Let's run that, and the result I get is 129313. And let's look at the result for the put option, American put option, with those parameters, 12931, and we have 12931 for the option valuation. So the results are robust and consistent with the Leisen Reimer paper. Okay, so to take a closer look then at how these trees are constructed and what potentially the benefit, well, the major benefit is in terms of the amount of time it takes to run the estimation. And just to see that for a moment, if we increase the step size, again I'm going to change this back to C, and I'm going to run this at 5000. Now the big downside with a static type memory, static type tree, is that the time it takes for 5000 steps is relatively long, and for in this instance the dynamic tree will be faster, and in the dynamic tree that's truncated, faster again. So the results we obtain here will the computational speed will tend to increase. And that can be important. So to run the static tree, it takes 3.29 seconds for 5000 steps. In this Leisen Reimer estimation, I'm getting 5.94. The same 5.94 here in the dynamic tree, but only taking 2.3, which is a bit faster than the 3.29 seconds. And then to compare the result for the call on the American option for the truncated tree, we're down here to 1.77 seconds. And again, that's faster again. So speed is generally considered to be something that is important and may also assist us here in getting to the higher step size. So for instance, if we put in a value here of 25,000 and put in a value here of 25,000 steps, which is kind of overkill, and run and put in a step size here of 25,000 steps and run as well, we would expect that of the three trees, the Leisen Reimer dynamic truncated tree will be the one most likely to reach that step size. Higher step size yields a higher level of accuracy, and that's why being able to make use of memory efficient can be important. So I'll just freeze here and wait until the results come back. Okay, so taking a look then, in the first instance in the static tree with 25,000 steps, basically the program was killed. It just didn't compile. The amount of memory required was probably excessive relative to what was possible. With the Leisen Reimer dynamic tree, with 25,000 steps, I get 5.9494. That took 52 seconds here, and almost 53. And with Leisen Reimer dynamic truncated, it took 38. Again, the result is the same. In terms of computation, the estimate for the American call option is the same, but the time required to estimate the dynamic tree was greater than the dynamic tree where the zeros were truncated. Now, to make sense out of what truncation means, it's probably worthwhile to take a look at a given tree. So I'm going to take a look at an Excel spreadsheet we had before for a call option using Cox Ross and Rubinstein. And this is a manual tree, and then I'm going to make the comparison between the Cox Ross and Rubinstein model and Leisen Reimer and look at what truncation means. So just in terms of the basic introduction here, in a Cox Ross Rubinstein tree, we estimated the value of the call, and then we use U and D, which we had outputted from a Cox Ross Rubinstein algorithm, and we generated the familiar binomial lattice, okay, where we have 15 time steps, and the time period involved in this instance is 6 months. Okay, so let's copy this again, and we'll build a Leisen Reimer tree. Now notice here with a Cox Ross Rubinstein, the values recombine, right? So for Cox Ross Rubinstein, the middle value here is 100, here it's 100, 100, and so on. In a Leisen Reimer tree, generally speaking, when you multiply U and D together, it doesn't make 1. So if you take the product of these two, it's going to be 1. And that's why we have this recombining lattice here for Cox Ross Rubinstein. Now to change this for Leisen Reimer doesn't involve a huge change, but I'm going to copy. So I'm going to take this, I'm going to copy this move, and I'm going to create a copy of a CRR called boundary small binomial tree. So it's this one, and then say create a copy, which it will do, and basically it'll just replicate exactly the same worksheet as we have here, but in the tab down below we'll have this title and then 2. So that's the original, and this is 2. And I'm now going to change that to, instead of Cox Ross Rubinstein, I'm going to say Leisen Reimer, LR, and I might take out the 2 here, delete, and put in 3. So it's a little bit more explicit. Now it's not a Leisen Reimer tree here, and the reason for that is the parameters, the risk neutral probability, the up, the down, and the discounted probability, the E negative or T, are not the same. Well, that will be the same, but these 3 will not be the same for Leisen Reimer. And to output the Leisen Reimer probability and the up and the down magnitudes, I just change the algorithm here from being from Cox Ross Rubinstein to Leisen Reimer, okay, and then I Control Shift Enter, okay, and the values have changed. And notice in this instance the value of the 3 here doesn't recombine. Okay, so the middle values are not the same. Okay, so in the next video we'll take a longer, deeper look here at the effects here in terms of the Leisen Reimer estimation on the shape of the tree and also in terms of the position of the zeros.